In this lecture, we will continue our look at the Earth's lithosphere, focusing this time on soils. Physical geographers have long grappled with the idea of a spatial relationship as it relates to soils and landforms, or at least the associated landforms. Specifically, they have looked at the relationship that exists between the nature of earthly soils and how landforms evolve or change over time. Our focus today is to look at how soils themselves form. We recognize the work of Vasily Dekochev, born in 1846, to be very, very important for understanding the global nature of soil. Dekochev and his students produced the first scientific classifications of soils. Additionally, they developed the first soil maps and the methods used to create those maps. Ultimately, the work of Dekochev and his students give us our modern methods for not only analyzing soils, but understanding something about how they form and change over time. And the change in this case is really focused on their material makeup and their chemistry. Modern soil geographers recognize soils as having a four-dimensional nature to them. They look at soils through the traditional two-dimensional profile format, where they're taking cross sections of landscapes and taking a look at the different kinds of soil horizons and their content. To this, they add a third dimension. In this case, they look at things spatially. They map them over kind of regional environments, and they superimpose characteristics associated with local ecosystems. To this, then they add that fourth dimension, in this case, a diachronic dimension, one that looks at how these specific soil environments have developed and changed over time. These dimensions, as is the case with much of what we have discussed thus far relating to the lithosphere, must be understood in a processual context. So soil genesis and its geomorphology become a very important factor as we start to look at not only the nature of soils as they currently exist, but how they have evolved and changed over time. Pedology is the science of soil genesis, its classification, and its distribution. It is a science of soil. In the field of pedology, we recognize another important 20th century scholar, in this case Hans Jenny, who in 1941 pioneered the functional relationships that exist between the biosphere and soil formation within the lithosphere. We can recognize soil and its genesis to be a kind of transition between the two of them. So, for example, Jenny, again a Swiss pedologist and agricultural chemist, in his publication Factors of Soil Formation, recognized that there is a linear relationship that exists between soil nitrogen content and, in this case, the annual precipitation that a region receives in terms of millimeters. What he found is that as the precipitation rate, and again, it's a very small scale measurement of precipitation, as the precipitation rate increases within a soil environment, the percentage of nitrogen within that soil horizon, and again, the soil horizon that's being impacted by the water translocating down through it or interacting with it, it will increase. So as the precipitation rate increases, so does the level of nitrogens in soil horizons. Another relationship that Jenny recognized, and again, a little less linear in nature, but there is a correlation in this case between two variables in his study, is that calcium carbonates, an important element or compound rather in the formation of sedimentary rock, things like limestone, also something very important to the oceanic ecosystems that we'll be looking at. These calcium carbonate levels within surface soils will decrease as the age of a soil horizon increases. So here's another kind of linear relationship, or at least a correlation between the chemistry of a soil, in this case its expression of calcium carbonates, and the age of the soil. So this means that older soils had lower percentages of calcium carbonate. To give you a little more information on this, a soil layer that, let's say, is 2 centuries old would have approximately 4% of its calcium carbonate by volume remaining. So with the contributions of Hans Jenny, we see a further development of pedology, in this case blending it more with the concerns of modern physical geographers. The idea that soils are not static, they are very dynamic, and they, as is the case with many other natural material systems within our earthly system, are constantly in a state of change, and that's something that we should consider as we study a landscape and the plants and animals that inhabit it. Well, let's move beyond this very brief history of how a soil science has worked its way into the work of physical geographers, and let's take a look at some basic concepts or basic principles that modern physical geographers will apply to a soil environment. And we'll recognize in this case 6 different concepts. The first is that a soil, or any sort of soil horizons, lie at the interface between the atmosphere, the biosphere, the hydrosphere, and the lithosphere. They're very dynamic. Therefore, to understand soils and specific soil horizons, we are required to know something about meteorology, climatology, ecology, biology, hydrology, geomorphology, and geology. So basically, there's a lot of science that will work its way into the study of soils from many different perspectives. A second concept is that contemporary soils, soils that are considered to be modern or recently historic, contain imprints or in a sense, evidence of pedogenic processes that have been active in the past. So by looking at a modern soil horizon, its physical and chemical nature, we can understand something about the processes that are currently at work within an environment, but then we also understand something about the history of these processes within that same environment. A third basic concept is that there are 5 external factors that we must study when we are looking at soil formation. We'll want to take a look at things like climate. We'll want to understand something about the living organisms within the local environment. We will want to study relief or changes in elevation. We will like to study the parent material that local soils are drawn from. And we will want to understand something about time. A fourth basic concept will take a look at how we analyze soil samples. So we will take a look at things like the characteristics of soils in specific landscapes by measuring particle sizes, the shape of these particles, the arrangement of larger soil bodies within soil horizons, the soil horizons themselves, the slope or the position of a soil environment within a landscape, and the age of a soil deposit. Fifth, we take a look at the pedogenic processes or soil forming processes that are at work within soil environments, both creating and destroying the stratigraphic nature of the soils themselves. So when you think about stratigraphy, you're basically looking at the kind of vertical layering of soils and soil horizons within a specific landscape. As physical geographers, as soil geographers, then we are interested in how those layers formed over time and how they continue to change even in the current moment. The sixth and final basic concept that we will want to associate with soil environments is more of a principle. In this case, the idea that there are very few old soils. Why? Well, because they can be easily destroyed, buried, or modified by shifts in climate or spatial shifts that are associated with the lithosphere and how it is changing and developing over time. What this means for modern secular soil scientists is that very little soil material can actually be dated beyond 65 million years ago, and that most soils and the land surfaces that we study as part of our understanding of those soils are no older than the Pleistocene epoch or the Ice Age. As I mentioned previously in this lecture series, the dates and the timelines that you will be exposed to as you continue on with your readings for this course and as you continue to engage this lecture material will conflict with potentially your worldview or many religious worldviews. It is important at this point to make sure that you are keeping these two realities mutually exclusive from one another. The perspectives that secular scientists have regarding the age of the planet and the history of the planet may be very different from your own. However, they do, in a sense, provide us with the curriculum not only of this course, but of a variety of courses within the physical and natural sciences. It is our responsibility then as students of science to be able to master and understand the currently agreed upon perspectives that scientists have regarding the age of the planet and the many processes that are at work as the planet continues to change and develop over time. This PowerPoint slide provides you with some of the terminology that we associate with the geology underpinning the development and change over time of our soil environments. What I mentioned just a moment ago was that we have a principle within our basic soil concepts that modern soils are not that old, and that they chiefly will be associated with the ice age. When you take a look at this diagram and you look at that kind of central column there labeled epochs, you will find that moving from the kind of bottom of the image to the top of the image, you're moving across time, and that in the middle of the image you see the epoch, the Pleistocene epoch, being identified. The Pleistocene epoch is when we see the majority of our modern soils in terms of their parent materials and in terms of their overall content forming and being transformed. This is an important time that we will be focusing in on because many of our modern landscapes are also understood through the lens of what forces or processes were at work during the Ice Age. Now we'll take a look at some of the variables associated with soil morphology. One of the things that is very important to keep in mind is that the, the qualities of a soil horizon, the physical qualities of the soil horizon, things we can see, things that we can feel, things that we can directly measure, these are very, very important in terms of how we classify soils and then ultimately how we map them out across the globe. One of the first things that we have to take a close look at are these particles or clasts that are really earthly minerals that compose soils and soil horizons. We realize that clastic particles, as is the case with what we saw in the class associated with sedimentary rock, come in varying sizes. We also realize that soils are composed of organic materials in various stages of decay. This includes living organisms and water and gases associated with that process of decay. These organisms and the water and the gases that we find in our soil horizons are generally stored within pores. Those pores will also vary in terms of their size. These also become very important characteristics or qualities that we will want to measure and record. So the size and the arrangement of soil particles and the spaces in between those soil particles or even clumps of particles become very, very important as we begin to understand something about the physical nature of our soils and the soils that we study. So let's take a closer look now at these clastic particles, and what we'll find is that generally they will fall into three major classes or camps. We have sands, we have silts, and we have clays. Soil particles are also known as soil separates, and again they fall into three principal categories. We derive these particles from processes of weathering. And as we take a look at these soil particles, we are really studying the texture of a soil. So when you use the expression soil texture, we're referring rather to the relative proportions of sand, silt, and clay within earthly materials. Generally, and especially it's the case when we are out in the field collecting soil samples, the soil texture will be understood qualitatively. Students will initially assess the texture of a soil by its feel. In the lab and under magnification, we will take a look at and measure the actual diameter of particle types within that soil sample. We will also take a look at the percentages of sand, silt, and clay that are expressed in any given sample. Pause the lecture for a moment and take a look at this table. What it will provide you with is how soil scientists study the specific properties of soil clasts or soil particles. It will also expose you to how each of these particle types behaves differently in a soil horizon. Beyond recording the texture of a soil, we will look at a few other variables as we are analyzing soil samples. One of those variables is soil color. Now, soil color, as you can imagine, is more often than not a qualitative assessment. However, we do use standardized systems of comparison in the field. Often these are referred to as soil color charts. The soil color chart will provide us with three additional qualities of what we are seeing in terms of the color of a soil sample. It will allow us to assess the hue, the value, and the chroma. The hue of a soil sample as it relates to the color refers to the composition of the light or the wavelength of light that emanates from a soil surface. In a sense, it's color. So something is red, something is yellow, something is yellow-red, yellowish-red, brown, so on and so forth. We also will assign a numeric value for value. This describes the darkness or lightness of a soil type. Generally, we will range this on a 10-point scale where 0 is black, and when we reach 10, we are in an area that we would consider to be white. Finally, in terms of color, we look at chroma. This refers to the purity or strength of a color. It too is ranked on a 10-point scale. At level 0, we find gray components in terms of the soil color, and then we move from there, moving into the darker hues as well. So when we are taking a look at the color of a soil sample, in fact, we are looking at three very distinct qualities of color: its hue, its value, and its chroma. The color of a soil particle, a sample, or horizon is ultimately a function of its chemistry and its physical makeup. Darker colors usually are associated with soil environments which have a very high organic content, whereas reds, for example, are associated with soil environments where we find a lot of iron and iron oxides. Another characteristic associated with the morphology of soils relates to an assessment of a sample's porosity. When we are assessing porosity, we are assessing the size and number of spaces that exist among a soil's clastic and non-clastic content. The measurement that we associate with porosity is usually a percentage score. So a soil with 45% porosity, for example, has 45% of its total volume composed of pores. Those pores generally will be filled with things like gas and water. Soils with low measurements of porosity, so they have very low percentage scores in terms of their porosity, are considered to be dense or densely packed. Finally, we take a look at the structure of soil itself. In this case, we look at the arrangement of primary soil particles, our sands, our clays, our silts. And we also look at what are referred to as naturally occurring PEDs, or natural aggregates of soil materials. Human-related aggregates, or even particles, are assigned an additional term, in this case the term clod. These also come in various sizes and forms that need to be recorded as we study soils and soil horizons. All of this information becomes a very important part of how we identify and classify and ultimately map soil horizons. Soil horizons in this case are distinct levels within a soil environment. They're distinct in relation to their depth, their texture, their content, and of course this includes um, the color, the porosity, and ultimately their structure. And ultimately, they are also distinct in terms of their chemistry. Soil horizons have their own unique structural nature, depending on the actions, natural or otherwise, that we associate with their formation and the formation of these aggregates or these PEDs. The internal cohesiveness of a soil environment, specifically a horizon, will be an important factor in terms of understanding its structure. Internal cohesiveness relates to the shape of soil aggregates and the particles within them, how these particles and larger combinations of particles are interlinking with one another, how they are locking together. It will also take a look at how this interlinking structure is important to how nutrients and other kinds of qualities within a soil environment move through that soil horizon. Now let's round out this lecture by taking a look at soil horizons and some of the basic principles associated with their development and how we classify them. Soil is composed of initially loose, unconsolidated material associated with the Earth's lithosphere. The general category that we associate, or term that we associate with this material, is regolith. Its relationship to its source, generally bedrock is the source, and its transformation through processes like weathering, transportation, and the admixture that occurs as soil horizons develop are all important characteristics that we have to consider and study more closely. All parts of soil are considered or recognized to be weathered or in a state of weathering. There are 7 commonly recognized soil horizons, and each of these soil horizons is formed in a sense by material and of course water carrying material in solution that is being translocated or moved, in a sense, from one location to the next. The translocation of soil particles, chemical compounds, and chemical elements, including the water that's very much a part of this process, is an important characteristic to also consider and monitor as we are studying soils and soil horizons. Translocated materials can move upward, they can move downward, they can even move laterally. Let's take a closer look at this diagram to better understand some of the basic principles associated with soil horizons and identify particular types of soil horizon. We'll start out with the horizon that you and I are often most associated with, or we're walking on, if it exists at all, which is the O horizon or the organic horizon. O horizons are organic in nature. They're composed usually of organic litter and material that's in some state of decomposition. Just below the O horizon, we have the A horizon. This will be a horizon that still contains a good amount of organic matter, usually associated with higher levels of soil moisture, but now it starts to demonstrate an admixture of minerals and the compounds associated with minerals from below. Transitioning to what becomes a B horizon, we find just below the A horizon an E horizon. E horizons generally will demonstrate colors, soil colors, that are lighter in nature, and they will have a very strong mineral content to their overall makeup. It's in the transitional E horizon that we start to see expressions of silicate clays, irons, aluminums, and of course quartz grains. As we transition through the E horizon to a deeper level or lower level, now we move into the B horizon. The B horizon is very mineralogical in nature. It's dominated by large accumulations of clays, which include iron, aluminum, and quartz. We recognize really the beginning of this removal process of carbonates. We also recognize a higher rate of compaction. So we'll have much lower expressions or percentage scores associated with things like porosity. The B horizon, as we compare it to those horizons above it, is also going to be considered a little more brittle in nature. Below B, we have the C horizon. The sea horizon is principally mineralogical in nature. It often retains much of the rock structure and content of the local bedrock and how it is being weathered to produce this regolith that's so important to the overall development of local soils. Next, we have the D horizon. D horizons are much more uniform in terms of their chemical makeup, and we do not see the same kind of leaching of minerals as we do with C and B horizons. The last soil horizon is the R horizon. It's the hardest in terms of its physical nature, and it is a soil horizon that is dominated by the parent material for nearly all of the other mineral horizons above it, in this case the bedrock. In the state of Wisconsin, for example, the parent material is dolomite. Dolomitic rock is very common in terms of its expression in both the D and R horizon in local soils. The R horizon is very, very deep. In fact, it's almost at the level of bedrock.